Okay, we're moving on now to the second part of the video lesson. Now, even though I'm going to try to move through this quickly, I'll try not to talk too fast because I know that doesn't help. Right at the very top of the first page of chapter 2.1 is a very important paragraph, and now that you've watched the first part of the lesson, I hope it's going to make a lot more sense. As they say, a relation is a mapping or a pairing of input values. Now you have a clearer idea, I think, of what an input value is with output values. So a perfect example, as we've talked about with input values, is tree age, and the output value is the tree height. Of course, it could be child age and child height or other measurements. The set of all those input values is the domain. Remember, input goes with X, goes with independent, goes with domain. All four of those things go together. Similarly, the set of output values is the range. Output goes with dependent, goes with range. A relation is a function provided there's exactly one output for each input. That goes back to what I said about it being like a calculator. I need to consistently get one and only one answer when I ask a particular question. So if I ask what 3 plus 7 is, it needs to say 10 every time. If it ever says anything but 10, I'm going to throw the calculator out. It's not a function if one input, any input, has more than one output. If one question that I ask the calculator gives me more than one answer, depending on what time of day I ask it, then it's not a useful calculator. And similarly, it's not a functional relationship between two sets of data if the set that I think is the inputs can't be relied on. If even just one of those inputs might possibly give me a confusing result, then it's not a functional relationship. Confusing meaning two to choose from. Okay, then we come to the second paragraph. Relations and functions between two quantities can be represented in many ways, including, well, here we come back to that word mapping, referring to mapping diagrams, and then these other ideas. Well, we've talked already about mapping diagrams. Tables, graphs, equations, and verbal descriptions. I hope these are familiar to you from one of the very first days we met. There's that list I gave you. Remember, I said algebra is a language, and that there are at least 5 different ways, certainly 5 ways we will study for representing or communicating with that language. And 4 of these 5 here are listed right here in this second paragraph of the textbook. Tables, graphs, equations, verbal descriptions. Tables, graphs, equations, and what I called words. Okay. 4th out of the 5 things you need to know how to do is how to graph a function that is an equation. Whoops, don't mean to be grabbing onto that. Now here I have gone ahead and started to collect the x values, and all I have to do at that point is figure out what the y values are. So if I plug in -2, I get -1. If I plug in -1 for x, I get 1, and so on. Graphing then becomes a simple exercise in plotting points, plotting the x-y coordinates, or the ordered pairs, in other words. So you should be able, coming out of this chapter, to do this with comfort. If I give you an equation, and I tell you it's a function, you should be able to report it back to me what the y values are for any given x value. Last couple of vocabulary terms, linear functions. So how do you know that a function is a linear function? Well, on a graph it's a straight line. Go back to what we just looked at. Now I said just earlier, you can't connect dots just because you have the dots, but it certainly looks like it would be the case that this is a linear function. And if we tried -1.5, or here +1.5, my guess is we would end up with a y value that's on this line. But all we have to do is plug that in. So a linear function on a graph produces a straight line. If it's an equation, you could write it in your old familiar friend the y equals mx plus b form. And I assume that's very familiar from Algebra 1. If an equation has an x squared term, an x cubed term, and the x to the fourth term, then it's not linear. And we'll talk a lot this year about the idea that when you have exponents on your variables, you move away from this idea of straight lines. But as long as x has no exponent on it, it's pretty reliably going to be the case that it's a linear function. Okay, so that's linear functions. The one remaining vocabulary term was function notation. Well, instead of calling it that old familiar friend, the slope-intercept, y equals mx plus b, just substitute in f of x in place of y. That's all function notation is. But function notation is important and useful because it's clearly telling you, hey, this equation is a function. You don't have to wonder whether or not it is. You don't have to do your own vertical line test. It's telling you that it's going to be. Other than that, this and that are one and the same, and therefore f of x can be substituted for y and vice versa. Finally, if I'm going to find the value of something called f of negative 3, all I do is plug negative 3 in place of x. That's what's going on here when it says f of x equals, and also says, so what happens when f is when you're looking at f of negative 3. I plug it in, I've got negative 3 plus 7, I get 4, and the way you would write the answer is right there. F of negative 3 is 4. Okay, there's your homework. So go ahead and write that down, bring that in, and we'll talk about it next time we have class.